the bonding wires. What do we have here? Yes. And diameter is what typically? No, that's not possible. 0.25 micrometers. No, that would be 25 nanometers. Yes. Okay, so here inside the package also we have that. So here that is silicon. What else do we have? Yeah. What did we select for the die attachment of that device here? We also have the attachment of the IC. How is it attached to surface mounted device? Sorry? SAC, yes. Question is, do we take, that's on the copper, the SAC must be here in between the thin layer, of course. What do we use for attachment of, what do we use for attachment of the chip? Do we take the same process or will we take another process? Yes, so what would be an advantage of taking the same? That would mean we can do it in one process. On the other hand, maybe other materials are less stressy. Yeah, so that of course the die attachment can have an influence on the stress level. We can have an adhesive that has a much lower Young's modulus. So that's our decision. What do we take for that? On the other hand, you selected something quite special. You put as a substrate, you put in a silicon substrate. That would mean already low stress. So maybe you could say you also take SAC here. Yeah. Yeah, one thing that is important for the package body of the surface mounted device, what do we have here? Yeah, so it's a molding compound and it is epoxy. Plus what? What's in the epoxy and why don't we use pure epoxy? Sorry? That's a reason, maybe not the most important, but what is a filler in epoxy of molding compounds? Yes. And why do we have it in? We also must give a reason why silicon oxide.
Maybe to match the CTE.
Yes, so that's the important point. By adding some particles, we can lower the CTE. Silicon oxide has, I don't know, around 1 ppm per Kelvin or so. So if we put in lots of silicon oxide, the CTE is lowered and we can reduce the stress especially on the bonding wires.
I have another question. In the script on the last side, there's accepted materials. Can we just take that materials, or what does this slide mean?
You can take these materials. The reason why I gave such a list is so in assembly and packaging, except for some materials like aluminum oxide or for few other materials, we can have well-defined properties, yes. But for most materials, especially if they are polymer-based, there is a wide range of possible properties. So normally you expect to give materials data which are 10% precise or so. That's impossible, yes, because in the market you have many possibilities. So I added this list so you have a hint what you could use.
Yeah, thanks.
Okay. Here the base is also copper of that device, and in IC very often we have a conductive adhesive. And what's the material of that conductive adhesive? So it's an isotropic conductive adhesive, and it's typically epoxy plus silver flakes, for instance. It also could be epoxy plus alumina if it's only thermally conductive. So when you talk about polymers, in most cases, when it's a hardening polymer, you will assume that it is something based on epoxy. But there is one material we have filled the package up here, so we have some fish swimming around. And in which medium does that fish swim? So in most cases, a polymer package is filled. And why is it filled? Yes, it's main reason is we avoid condensation, and also when it's hollow and temperatures are changed, and if there would be no opening, that would be like a thermodynamic machine, so it would expand and contract and so, and that would not be good. So it's best is it's completely filled up, and that is silicone. So it's written like silicon, but it has an E at the end. The reason is it's like silicone rubber, but still softer than a rubber. So really like some gel or such a thing. And in that way, it fills it up. And as it is a gel, it can self-repair because it flows. And what else? Such gels have also high dielectric strength, for instance. So in that way, it also protects, and because it's so soft, it builds up only a very little stress. Okay, so maybe we just add why we have these materials, what would be a reason. Silicone adhesive, it is stress free. Copper, nickel plated, good. Lambda, where lambda is the heat conduction. Copper, iron 2, with nickel gold, good machinability, for instance. PBT, or let's say PA6, it's cheap. Gold, why do we use gold? We do ball bonding, and also it is corrosion resistant. Molding compound, epoxy, silicon oxide. I would say it's just a good protection. Oh. Why did we take silicon? That has a, sorry? If you want to do molding, there is no alternative. There are roughly several hundreds of epoxy molding compounds in the market, so you can select from one of them. But for molded packages, there's no alternative. It's always epoxy with some silicon oxide plus something else, but that's the main thing. So here, the silicon, here we had said low CTE. SAC for surface mount technology. Normally, as an answer, I do not like it's a standard material for such things. You might also say that for wire bonding or so, but I don't like that because everybody does it is not really a technical reason, but for surface mount technology, in fact, there is no alternative than using SAC. Did we forget something? No, I think we mentioned all of the materials. Now the next thing would be the sequence of production. In some way we had it here, but no, here. Package for IC, substrate type, package for module, assemble sensor on substrate, assemble IC on substrate, mount substrate in package, interconnect a sensor. Maybe it would be good for repetition to do say it explicitly. So first of all, the SMT is the surface mounted device is purchased. That would be one thing which can be done. This surface mounted device, which is a QFN. Yeah, let's have a look at it. We have something like a lead frame. We have a chip mounted on top. We have the chip itself. Yeah, there's one thing we forgot. That's an aluminum silicon metallization that is typically here and also here in most cases. The chip production in that case we don't deal with. So we have the lead frame. CID of lead frame. Then we can, for instance, stamp it and with a tool. Then we are already finished with that. The next is we put on an adhesive, for instance, print. Pick and place. Chip. Harden. Adhesive. How do we harden it? Do you have some idea? Yeah, that's thermal hardening typically. Yes. Oh, no. Okay, let's just say 150 degrees centigrade. So it was in the middle of what you said, 1 hour, for instance. So then what's the next step? The chip is attached. No. Yeah. No, we have given some examples, yes. But if you have something like, there was one example, 200 degrees centigrade, a few minutes. So the idea is if you go down by 10 degree, you always have to double, yeah? Just as a guess, so let's say 2 minutes, 200, 4 minutes, 190, 8 minutes, 180, 6/4 of an hour. Yeah, that is something, but don't nail me. It can be quite different. Yeah, it could also be 3 or 4 minutes or so. Yeah, I want to see a reasonable value. Let's say it that way. Yeah. Okay. And so also that value is consistent with what I said. Yes, with the minutes for 200 and hardened adhesive. But the next question was, what do we do next? You talked about conductive, but yeah, so you talked about wire bonding. So we said with gold 25 micrometer. We will have wire bonding another time. So here you don't have to specify parameters. Yeah. So wire bonding, then we go into the molding. After the wire bonding, put assembly in mold, reactive transfer molding. What's a typical time and temperature of such molding? Typically a little more than for the adhesive. For instance, let's say an example was and 2 minutes, but the mold must be baked, so post hardening. And that's typically 4 hours. So the hardening is complete after that. Also, you could say, for instance, if you want, here you could take the time shorter, because when you have that adhesive here, it's still hardened, or the hardening is finished in that process here. The molding temperature and the post-hardening temperature is normally the same, yes. And then as a last step for the device, we can take the surfaces, and they are, for instance, tin plated. For instance, with chemical tin. So solderability is preserved. Okay, that would be the surface mounted device. So we could say that is achieved here. Of course, we also must produce the sensor chip. I wanted to go in here. So that we should also do relatively briefly, because that's not a lecture on MEMS technology, but we should know how the sensor is produced, at least in gross steps. So we have the substrate wafer. Here we could produce the substrate and the structure in surface micromachining typically. So surface micromachining, cap wafer. What was the process to produce the cap wafer here? Yes. Sorry? No, I'm talking about this here. No, but not that. That must be hermetic. So we can either use a glass, or if it has these angles, it is etched with some caustic acid. So it's anisotropic etching, yeah, and that means bulk micromachining. So that's anisotropic etching. And the last thing is the cap is put on, and we close it with, so we must heat it out. And wafer bond. For instance, with glass frit or such a thing. There are many possibilities, but we should at least have an idea how it is produced. Okay, so we got both parts. As both parts are purchase parts, we just must have a basic understanding how they are created. And then yes, important is the substrate. On what? You're talking about the SMT device or about what? No. The passivation is part of the chip. And it is, when the chip is produced, there is a passivation on it. Here not, no. So, substrate. As you insisted on using silicon, it's a little special how we produce here the substrate. We have a silicon carrier. Question, how do we get the metallization structure here? Also, we cannot just have 1 or 2 micrometers of copper on it, because why not? Because when we would solder on 1 micrometer of copper, the copper would be away and the solder would just dewet from the chip. So it must be a thicker copper layer. How can we produce structured, thicker copper layers?
Maybe sputter?
Yes, let's discuss about it. Direct copper bonding is in principle possible, but you cannot get features that are fine enough for surface mount technology. That is not possible. So you said sputter. Sputter what?
Sputter the copper.
That's not wrong. So we have the silicon. Let's make a normally you don't do it for such thin copper. And as we have seen in etching, you always have structures that are much wider in pitch than thickness is. So I would say when you do it, we can sputter. Let's start it that way. Let me say that's not the real standard process, but you could do it. So you sputter. That is you sputter copper, but what will you do in order to improve adhesion of the copper to the silicon? You first put on a layer, and that layer could be something like titanium or so. So here you have 1 micrometer, but that's too thin. How can we get a thicker structure? So in the end, we want to have something in the location where we put on the QFN. We want to have for instance, such structure. How can we get that? Print with what? No, I would do it something else. And that's a process which we will have to see some maybe later on in another connection. So we put on a photoresist. So yes, we put on a photoresist and then we electroplate into the resist. Yeah. And then we plate a little of tin. Oh, wrong color. Okay, so let's start. We have the silicon carrier, sputter, let's say titanium, 20 nanometer or so, just it sticks better. Copper 1 micrometer. Then we put on a photoresist. That resist is that resist is, for instance, spin on or expose, develop. So we have openings in the resist, yeah, here. And then we can electroplate copper. So that's the same like it is done in printed wiring boards. We electroplate copper plus tin. The tin is only a edge resist. Then we do something which is in English is called stripping. And then we back edge what do we back edge? No, that makes no sense. The tin is an edge resist. The tin is on the thick copper in order to yeah, so here we have the copper. So I put the so we have here we back edge the copper and the titanium. But now we have to look out when are we finished with the board now? Are we finished or not? We are presently developing the or making the substrate. What's missing in the substrate? When you look at the image. Sorry? I'm talking about this here. What is that? That's yes, it's gold and nickel. Also, we must back edge the tin, of course, and then we do chemical metallization. Nickel plus gold. For instance, nickel 2 micrometer and gold, let's 0.3 micrometer or so. That's quite different, but it's a thin gold and a thicker nickel. Reason is via bondability. So we have and also we have solderability. So that's the substrate. So it's a little, yeah, normally we don't take silicon as a substrate, but we could take, for instance, thick film, which with a screen printed structure. And when you look at the lecture notes on ILIAS from previous years, you will probably see another process for making the substrate, but again, the design is your choice, yes, and there is not a single way to do a design, yes, for each, yeah. Yeah, we had justified it with very low CTE. And that means we really don't have big stress on the gyroscope, which is also good. So in fact, I must say, I have not seen such a design with a silicon substrate, but again, I gave you a task, and as long as it's and such solution is not wrong, yes. If there would be some other restrictions where I would write, but silicon is not allowed as a substrate, then it would be different or so, yes. But here, it's an option. So that was the substrate. So then, come on. We have that. We have that. We have the substrate. What about making the package body? Okay, let's start. So the package consists of 3 parts. It's a polymer body. We have the heatsink, and we have the lead frame. Yeah. So we have the polymer body. We have the heatsink. And we have the lead frame. What will we start first? I would say the lead frame would be best. Normally, what's always the first step when you make a part? Yes, design. CAD. In order to make a lead frame, how can we make a lead frame? So in our case, it's a metal structure having a big sheet for many packages simultaneously. They cling together. Yes, how do we produce the lead frame? Yeah, that could be a possibility. That's not wrong. But normally they make it somehow different. They take one tool in a stamping machine, and that is stamping out or punching away what you don't want to have. and at the same time bending parts. So if they have bent inward or are on several layers or so, so it's you first design, make a CAD for a stamping bending tool. Yeah, bending, punching. And which other tool do you need? The package body is made of polyamide. So you need a mold. Okay. And for what else do we need a design? That design is for the heatsink. Okay. So the next step is production. We can have so for the lead frame, we do the punch and bend. Later on, after that, we can already make the plating. Yes, for instance, at that step, we can put on the nickel gold, but we can also put it on after the whole thing has been injection molded. So we punch and bend the lead frame. Then how is the heat sink produced? So it's a thicker copper. How can we produce that? So it's done by machining, drilling, and nickel plating. So we have the heat sink, and then we put both lead frame and heat sink into the injection molding machine. Injection molding machine. And then we do the injection molding. Typically, for instance, the material we mold, so has something like 250 degrees centigrade. The parts in the tool, they have something like 80 degrees centigrade. And after the molding, as I said, we can still plate with nickel and gold, for instance. So in that way, the package is produced. Polymer body. One part I forgot. It's not so important, but it's the lid that needs a separate tool. And of course, it's injection molded separately, but the lid is just a piece of polymer material we need to put on as a cap. Okay, so in that way, the package is finished. Now let's have a look back. What we have is also the heatsink, we have the package body, we have the coating here, the nickel gold. Here we even have a nickel plating or even nickel gold in our process. What else is missing? Now we have to put the parts together, and the first thing would be to put the two devices onto the substrate. Yes. How would we? As we put it, we would coat both sides. Yeah. Yeah. With the nickel, I would say it's reasonable to do it that way. The nickel normally was blue. Okay, what's the standard process we had here? Yes, how do we do that? Is there still a part we need for that? Yes. So CAD of here we call it a stencil. That is a mask for printing. What's the process to produce it? Already mentioned someone such a process. So it is laser cut. Then we place a stencil on board, so on substrate. It would be good to make a small sketch here to show how that looks. I just take only one color here. So a stencil is put on here. Ah, no, that shouldn't be here. I know it should be. So we have, yeah. So we can we have the paste. And when we move that squeegee here, we fill these openings up with the solder material. So what's the next step? That's the last thing we do today. That is we stencil print. Then we pick and place chips. And then we have the soldering. And for the soldering, we have a certain profile we need, but that we will do in the next session. Okay? The blue. That's good. So that there is nothing here in between. Copper is here and here. What you could do, we didn't treat it, but normally it would be an advantage if we have some solder resist here. Yeah, to be correct, we should have done it on the I know that was nonsense. So we have the metallization. Ah, yes, yeah, we already have the resist. Ah, yeah, solar resist. So here. Yeah, the reason is I didn't remove these layers here. No. That's a silicon. So that should be correct now. Spin on resist. Expose and develop. In that way, we even have a solder resist, which is of great advantage in the soldering process. Yeah. Yeah, a solder resist is a photoresist. Yeah. No, both are photoimageable, but they are chemically different. Solder resist, no, I think normally a photoresist is a polyester, as far as I know. And for solder resist, you can have acrylic polymers, or you can have epoxies. Yeah. And okay, so we're not yet completely finished, but almost. And we'll meet on Friday now. Okay. Sorry. I didn't say you can't use it. You can use it, of course. But just here in the exercise, I cannot just do any options which are possible in parallel. But you mentioned it, and it is okay. Yes. In terms of accuracy, the best is etching. Again, the accuracy is not extremely high, but it is sufficient. Yeah. Okay. Yeah, you look on Ilias and you find it. Really? I have a look, yes. If you don't find, send me an email, please. Yeah. Yeah, but I think I should have